Okay, guys, so we are going to talk about how everything kind of comes together, right? And so we talked about basically where we get the major macromolecules that we can utilize for making energy, specifically making or storing energy in the form of adenosine triphosphate or ATP, and then using that later. And so the first question is, where does glucose come from in order to start glycolysis? And that comes from basically two. Of course, it may come from essentially eating different forms of, or eating carbohydrates, glucose specifically. But it can also come from essentially body stores. And so there's two major processes in our body. There's one that's called glycogenolysis, and gluconeogenesis. Glycogenolysis is basically the process of breaking down stored glycogen into glucose. That basically goes into glucose, right? So glycogen is basically if you eat food and then you have this extra leftover amount of glucose going around in your bloodstream, then your body will trigger to store it for later. And it goes into this basically process of taking glucose and putting it into a molecule called glycogen. And that process is what's called gluconeogenesis, right? And once you basically go some time without having any glucose or lower levels of glucose in your blood, then it'll start breaking it down. So it uses these two processes to make sure that you always have an available source of glucose in your body. Glucose as well. Now, we don't just eat carbohydrates, we also use fat. And so fat can be, yes, used to basically make ATP. And so the process of breaking down fat is what's known as lipolysis. And it's done by lipases. And basically what it does is it forms what's known as glycerol and fatty acids. Those are the two structural components of a triglyceride. Now, fatty acids can be further broken down into acetyl-CoA. And if you remember, acetyl-CoA is the pre-molecule that goes into the citric acid cycle, or the Krebs cycle, right? And the process of taking these fatty acids and breaking them down into acetyl-CoA is a process known as beta oxidation. We're going to go into this more and actually look at some of these pictures more later. And the last thing is, can proteins be utilized for cellular respiration? And hopefully, again, you realize the answer is yes. And it can be broken down into a lot of different things. For the most part, you can see them being broken down into acetyl-CoA again. Now, this process is known as deamination. And basically what it does is it removes, and deamination is basically talking about removing what are known as amine groups. And this is what an NH2 is, what an amine group looks like. And so you can break down proteins to feed straight into the Krebs cycle, and then a deamination is going to produce basically byproducts, because then that amine group is changed in the body or processed to NH3, which is ammonia. And then this gets further processed into this crazy looking molecule here. And this is what's known as urea, right? And then you'll get rid of it. So during normal bouts where there's plenty enough of food to go around for everybody, there's no problems. But in cases of things like starvation, it can be a problem, right? And basically, your body prefers glucose. It's the easiest to break down for the optimal amount of energy. And it requires the least amount of energy to make energy from cellular metabolism, because you're not having to break other molecules down and convert them, a process of catabolism and anabolism together to create these molecules that feed into cellular respiration, which is what you're having to do when you take things like fats or proteins. So to kind of look at some of these things again, here's when we're talking about where does glucose come from in order to start glycolysis in the cell. And so you can see the two major aspects here is glycogenesis and glycogenolysis. And so basically, when we're looking at here, you can see here you have a lot of blood glucose. And so you are going to basically synthesize glycogen here. And so glucogenesis here, basically you take these small molecules of glucose. This, of course, is you have more glucose there than you need the need for ATP. So basically, you have, if you look at glycolysis, the very first basic enzyme, one of the very first enzymes is hexokinase. And so through here, you make glucose 6-phosphate, which, if you remember, that's a process. There's several steps here, right? That makes the hot stepsister. Well, instead of continuing throughout, you'll see that it changes a little bit into glucose 1-phosphate. And then from here, using the enzyme glycogen synthase, you're making the storage molecule. Now, glucogenolysis, and you can see lysis here, genesis as in building or creation, right? Lysis as breaking down. You can see you have low blood sugar here. And so you have these stores of glycogen. So this enzyme called glycogen phosphorylase is going to start breaking it down into the opposite direction. And basically you have this enzyme, glucose 6-phosphatase. You can see it's present in the liver, kidney, and intestinal cells that are going to help break it down even further and release those individual glucose. So this is how you're basically regulating blood sugar and cellular respiration in the body to allow it to continue. And so on here, glucolysis is basically, or glycolysis, right, is what you do for ATP. Here's a quick summary of what happens. Glucogenesis is a process when you're basically taking glucose when you have excess amount of glucose and you don't need to use all the ATP to make the storage. Glucogenolysis is when you're taking the glycogen store and making it so that you can release sugar when sugar is less. And gluconeogenesis is basically making glucose from non-carbohydrate sources. This takes a lot of energy to do. And so this is going to talk a little bit about what happens during starvation.
Medically speaking, starvation occurs when a body doesn't get enough calories and nutrients, whether brought on by poverty, famine, being lost at sea, voluntary hunger strikes, or medical conditions. The physiology of starvation follows the same process no matter the cause. And it really is a process. It takes time to starve to death. Without oxygen, our bodies shut down in 5 or 10 minutes. Without water, we can last maybe a couple days, a week at most. But depending on the circumstances, a person might go as long as 2 months without any food at all. During this time, the body passes through 3 distinct metabolic phases as it desperately tries to stay alive until it finds food again. Phase 1 is where your body picks the lowest hanging fruit, energy-wise, through glucose burning. In your normal, well-fed state, your body breaks down glycogen molecules to produce glucose, the friendly carbohydrate that keeps your cells well-fed and functioning. The average person can typically go about 6 hours after feeding in the glucose-burning phase before they start feeling hungry and probably grumpy. At that point, your body has burned through all that lunchtime glucose and is turning toward fatty acids, the building blocks of fat molecules stored in your tissues to fuel itself. This switch kicks off the first big metabolic shift as your body enters phase 2 of starvation, fat burning. The fat burning phase can last from days to weeks. During this stage, called ketosis, our livers metabolize fatty acids into smaller fat chain derivatives called ketone bodies. They replace glucose as the main energy source. These compounds come in 3 different water-soluble configurations that move from the liver to the heart, brain, and other tissues during periods of fasting to try to keep things going. Some people, like hard-training triathletes or bodybuilders or those on a super low-carb, high-protein diet, may be in ketosis pretty often. It doesn't mean they're starving, it just means that their bodies are running differently because either they're not eating enough carbs from which to get glucose or they're quickly burning through them. But if you're thinking that eating butter-covered bacon to burn body fat sounds like a good deal, you should know your brain might be less than amused. Your brain can't directly use those fatty acids as fuel because they're too big to squeeze through the blood-brain barrier. And our brains are a big energy suck. They demand about 25% of our stored energy to function properly. They're kind of greedy like that, needing about 120 grams of glucose a day to stay happy. That's like 3 cans of Coke. It's like 4 cans of Coke if one of them's diet. So in your first day or two without food, while the rest of your body starts fueling itself on fatty acids, the brain drains the last bit of stored glucose until it really runs out. But you probably noticed that no one dies after just 2 days without food. That wouldn't make very much evolutionary sense. Luckily, your brain is smart and it has a backup plan. Within a few days of no food, your brain recalibrates its glucose requirement from 120 grams to about 30 grams, and it changes the menu. The brain now starts eating those processed ketone bodies, which, because they're smaller than fatty acids, can get through the blood-brain barrier. This is a great evolutionary trick to keep us alert enough, no matter how hungry we are, to continue to look for food. But even if you are semi-alert, you're definitely not in a good mood. As a hungry brain is continually deprived of vital nutrient, it gets to feeling depressed, anxious, lethargic, and socially withdrawn, and starts to have trouble concentrating and comprehending. The third and final phase of starvation begins when all your fat stores are burned up and the body switches to using its final reserves, proteins. This phase is marked by rapid muscle depletion as your body cells start to break down their own proteins into amino acids, which your brain now gobbles up. Proteins are essential for proper cell functioning, so things go downhill pretty quickly as your body starts eating itself, basically, in a process of internal self-cannibalism called catabolysis. Still, your ever-optimistic body tries to run damage control by eating up your least vital cells for as long as possible as it holds out hope for more food. But after weeks of no food, once your body has burned through all available glucose, fatty acids, and protein muscle mass, it's got nowhere left to look. and the end is near. Keep in mind that by this point, your body is so grossly deficient in vitamins and minerals and has such a weakened immune system that just about anything could kill you. In the end, the ultimate cause of death during starvation is often cardiac arrest due to excessive tissue degradation. The heart simply can no longer support itself with such limited resources. It's enough to make us all, I hope, really appreciate everything we eat, at least for this one day. Thank you for watching this episode of SciShow. If you have any questions or comments or ideas for us, we're in the comments and on Facebook and Twitter.
Okay, so that should give you a bit of an idea of how starvation works. And so basically there are 3 stages of metabolism of energy-containing nutrients, right? So stage 1 is the actual digestion in the GI tract, lumen. And at this point, they're going to absorb these different forms as, i.e. proteins, carbohydrates, and fats. And they're going to transport them via blood to tissue cells. So as you can see, for the protein, basically we're going to utilize the amino acids from them. From carbohydrates, there's glucose and several other sugars that we're going to get from that. And then, of course, the most commonly form of lipids that we have are triglycerides, and they are going to divide into glycerol and fatty acids. From here, we go into stage 2, and this is basically when you have both the process of anabolism and catabolism happening. And what do I mean by this? I say, well, if you look over in this area that says proteins or amino acids, basically, they're not just going to automatically make these molecules when we're talking about amino acids being there. What they're going to do is they are going to have to change their form of monomer, you can see, to make it into an acceptable molecule that glycolysis or cellular respiration in general can utilize. And so you can see on most of these that you're getting an amine group leaving. This is in the form of ammonia. And you can say it can go into glycolysis, the precursor to the Krebs cycle is acetylcholine, and the less frequent being going in directly into the Krebs cycle. Of course, here with glucose, you can either go into the storage molecule for glycogen, or you can basically see that it is breaking into glycerol, going into glycolysis, specifically being glycerol 6 or G3P, glycerol 3, aka the hot stepsister. And the fatty acid is actually going and changing and becoming acetyl-CoA, and then they'll go through. And the last stage of this is oxidative breakdown. And so basically, at this point, most everything has gone into some other stage, except at some point, sometimes infrequently, proteins or amino acids can go into the Krebs cycle. And this is a process that you start making ATP through essentially reactions. So you can see at some of these that the anabolic reactions are happening when you're actually making glycogen stores or proteins or fats coming together. And essentially most of the catabolism happens when you're starting to break down these to actually form these molecules that go into the cellular respiration. And so let's focus on lipid metabolism. Lipids actually provide a greater energy yield than from glucose or protein catabolism. And essentially on here, fat catabolism yields about 9 kcals per gram. If you're looking at carbohydrates or proteins, it's normally about 4, so you're getting almost double the amount of energy here. And this is something that's not new. We know that you can get a lot of calories from fat. If you try to eat a lot of fat, then you're going to take in more calories. It's transported in lymph as the chylomicrons, right? It doesn't get absorbed straight into the bloodstream. It's too big. So it has to go through the lymphatic system. It's actually hydrolyzed by endothelial enzyme into, as we know, fatty acid and glycerol. And it's done by an enzyme called lipase. So you can see there that it's breaking down. The glycerol will go into glyceraldehyde 3-phosphate, which is a glycolysis intermediate. That's the one that happens after aldolase breaks glucose in half into the two different 3-carbon entities. And then it can be further processed through glycolysis to pyruvic acid and mediate through the cellular respiration. Now on here, you're going into where it's only half of glucose, right? It's only this one molecule. Remember when we talked about glycolysis earlier that we had it broke in half too with aldolase. So this is only showing you, or is only going to produce about half the amount of ATP that a full molecule of glucose would, because it's only one side of it. So this yields about 15 ATPs per glycerol. So it's about half. Now the fatty acids, as you can see, goes in, and you can see coenzyme Q along with ATP water. It's going to make these two coenzymes, right, in the process of feeding it into acetyl-CoA. And these guys later will go to oxidative phosphorylation. This process is known as beta oxidation. And basically, this acetyl group that we're going to make binds with this coenzyme A to form acetyl-CoA, which then can enter the citric acid cycle, right? And basically, it's referred to beta because it takes off 2 carbons are broken off of this chain. And so this is the process of basically lipid metabolism. So when we're looking, you can take either adipose stores of fat or dietary fat, and we're going to get triglycerides from them. So you have lipolysis, right? Lipolysis is the breakdown of stored fat into glycerol and fatty acids. It's the reverse of what's known as lipogenesis, which is when we synthesize triglycerides. Which, if you go over here, if you look, we have lipogenesis here, and this is when we can actually synthesize triglycerides, and that occurs when cellular ATP and glucose levels are high. Why it keeps doing this? Sorry guys for that little guy that's up there. I'm going to have to fix that here in a second. So when you have high glucose levels, lipogenesis will happen. So dietary glycerol and these fatty acids are not needed for energy. If they're not needed, they are stored as triglycerides. 50% is stored in adipose tissue. The other 50% is deposited in other areas. So basically, if we need to, we can take these and feed them into glycerol. Now, if we want to make energy, or if we need to, right, then your fatty acids can be, glycerol can be fed into here into glyceraldehyde 3-phosphate, which I talked about earlier. Fatty acids get broken down to acetyl-CoA through beta oxidation. Now, beta oxidation happens in the mitochondria. And we talked about this a second. It's when your fatty acids are broken down into these 2 carbon acidic acid fragments. And in this process, we're going to make those electron carriers that will feed into cellular electron transport, right? And that's both the Na, we're going to end up making NADH and FADH2 through this process as well. And then basically what happens from here, it's going to feed into the citric acid cycle. Now the problem with this is, in order for the citric acid cycle, if you remember, it feeds into there and it needs an intermediate to basically combine with, right? Over here, called oxonyl acetate. If there's not enough oxonyl acetate there to combine with, to continue around and make energy, then that acetyl-CoA can accumulate. And basically, as this accumulates, the liver is going to trigger ketogenesis. And that's going to make what we know as ketone bodies. And so example of this is acetoacetate or acetoacetic acid, beta-hydroxybutyrate, or beta-hydroxybutyric acid, and most common that you guys will know is acetone. And so accumulation of these ketone bodies in the blood can be bad. It can lead to ketosis, which a lot of people are striving for all the time, right? Ketosis is basically pretty common in starvation, unwise dieting, or in diabetes mellitus. Ketone bodies are excreted in the urine, so a lot of times if you're on these diets that promote ketosis, you can test it using urinalysis strips. Now, why this can be bad and why when you're using these diets that you don't want to stay in ketosis is that ketones are extremely acidic, so the buildup of these molecules can actually lead to metabolic acidosis, which if you've taken my class in part 1, you already know that this can cause the pH levels of the blood to become dangerously low. A lot of times you can figure that someone is a patient has ketoacidosis by also smelling their breath. It's very, can smell fruity, and that's from vaporizing the acetone that's in your body. It's trying to get rid of it in some way. Breathing becomes rapid also as lungs try to release CO2 because, as you know from acid-base balance, which we're going to talk about in this next section again, that releasing CO2 can help to reduce the acidity of the blood. Carbon dioxide mixed with water creates carbonic acid, and carbonic acid is an acid, so it'll reduce the pH. So this is one thing. If you have metabolic acidosis, this is created from these ketone bodies, and your body tries to use their respiratory system to get rid of it. Now, lipids can actually also help to make structural material. So, lipids are also important in phospholipids, which help to create cell membranes in the myelin of nerves. Cholesterol is used for cell membranes and steroid hormone synthesis, which is also considered a lipid. And you can see here that essentially you can make cholesterol from here. And basically we synthesize cholesterol from acetyl-CoA. And in addition to making steroids from cholesterol, which cholesterol looks a lot similar to things like testosterone and estrogen, you can also, cholesterol is used to form biosalts as well. So structural material is very, very important as well. And this is just kind of breaking down the process of beta oxidation converts fatty acids to acetyl-CoA. Lipolysis is breaking down lipids to fatty acids and glycerol. And lipogenesis is when you form lipids from acetyl-CoA and glyceraldehyde 3-phosphate. And so this last part we're going to talk about is protein metabolism. And proteins are deteriorated, so they need to be continuously broken down and replaced. Amino acids are thus recycled into new proteins and different components. Proteins are not stored in the body. When their dietary proteins are in excess, basically amino acids are either oxidized to energy, which is what we've been talking about, or converted to fat. So really the goal here is to produce molecules that can be used for energy. In the citric acid cycle, or converted to glucose. How they do this is the process known as deamination. And basically, amine groups are removed and then converted to pyruvic acid or one of the ketone acid intermediates that you see in the citric acid cycle. So let's look at this really quick. So there are three main events of amino acid degradation. Right, number one is transamination. And so basically here, many amino acids can transfer their amine group to basically what's known as an alpha ketoglutarate acid. And then basically it transfers that into what's known as glutamic acid. And so basically a lot of these original amino acids that we have here get changed into a keto acid. And so basically what's going to happen with this guy is that you can see once this amino acid and this keto acid combine together, the keto acid can be modified to fit into the TCA cycle, right? And then you're going to go in this other part of this reaction, the amino acid in form of the glutamic acid or result, ends up going through this oxidative deamination here. And so you're going to remove part of the amine group, right, from here. And then you have the ammonia, and this happens in the liver, and then that's going to be converted and combined with CO2 to form urea, and then that's going to be basically excreted. And the keto acid that becomes modified, this is the third one, right? It's going to basically turn into a metabolite that can easily enter the citric acid cycle. So the major metabolites that are produced here in this keto modification are things like pyruvate or pyruvic acid, acetyl-CoA, alpha glutaric acid, and oxonal acetate acid. Now, just to let you know, glycolysis is reversible. So this means that any of the things like pyruvic acid metabolites that are formed could be converted back to glucose. And so this can contribute to the gluconeogenesis. So let's see, this guy here could go back to, it's reverse, so it could go back to glucose, right? So this is what would lead to gluconeogenesis. Remember, and that was a process of making glucose from other entities besides a carbohydrate. So transamination is just transfer an amine group, and that's going to be from an amino acid to the alpha ketogluteric acid, generating glutamic acid. And then from there, you're going to get the oxidative deamination, which is removing the amine group. And so this is going to go off as ammonia and basically combined with carbon dioxide to form urea and water, and it's going to leave, right? It's excreted in urine. And basically the urea cycle helps to rid the body of toxic ammonia. That's this process. And this happens from glutamic acid. That is going to be what helps essentially regenerate the alpha ketogluteric acid for transamination to continue. And then from transamination, you'll get the keto acid modification to help produce the metabolites that are necessary for the citric acid cycle. And so I'm going to stop here, and this last part I'm going to talk is all going to be about metabolic states. So at this point, I'll stop with talking about